This is Algebra Lesson 7-2, multiplying powers with the same base. Now you can use a property of exponents to multiply powers with the same base. So let's look at something for a minute. If we had 8 to the third times 8 to the second, that would be like saying 8 times 8 times 8 times 8 times 8, which there are 5 eighths, so that would be 8 to the fifth power. If I have x to the third times x to the sixth, that would mean I'd have x times x times x in the first parenthesis, and x times x times x times x times x times x in the second parenthesis. If I counted up all my x's, I have 9 of them. Now, if you pay attention to this, you would notice that the sum of the exponents of the expression equals the exponent of the answer. For example, up here, 3 plus 2 equals 5, which is the answer to my exponent here. And here, 3 plus 6 equals 9, which is the exponent there. That leads us to a very important property of exponents, which is multiplying powers with the same base. So for every non-zero number a and integers m and n, a to the m power times a to the n power is a to the m plus n. An example of that would be 5 to the third times 5 to the fifth becomes 5 to the 3 plus 5, or 5 to the 8th power. Okay, we're going to use these properties of exponents a ton this chapter, and then they will continue on in the next couple of chapters, so it's important that you understand how they work. So let's rewrite each expression using each base only once. So I have 2 to the third times 2 to the sixth. Since each base is 2, that's what it means by writing it with each base only once. The only way you can combine them is you have to combine properties with the same base. So I have 2 to the 3 plus 6, which makes this 2 to the 9th. Okay, I could multiply out 2 to the 9th, but it didn't ask me to. It just said to rewrite it using each base only once. It didn't say to simplify it. Number 2 here, I have a to the 4th times a to the 7th, which would be a to the 4 plus 7, which makes this a to the 11th power. And here we have z times z to the third times z to the fifth. Now remember, z is the same thing as saying z to the first times z to the third times z to the fifth. So we have z to the 1 plus 3 plus 5, which makes this z to the 9th power. Don't forget that if a variable is taken to the, if it doesn't have an exponent expressed, it's always taken to the first power. Okay, let's look at a couple more examples. Let's say we have x squared y to the third times x to the fourth y to the fifth. Now we need to make sure we combine only those things that have the same base. Okay, so I have my x's need to go with my x's, and my y's need to go with my y's. So here I would have x to the 2 plus 4 and y to the 3 plus 5. So that's x to the 6th, y to the 8th. And this last problem here, we do have to pay attention to sometimes we have negative exponents. So we have a 2 to the 4 plus negative 3. 4 plus negative 3 is 2 to the first, so we could write this as 2 to the first, or just 2. All right. They mean the exact same thing. Now I snuck problem number 4 in before I really got into the importance of when variable factors have more than one base, be careful to combine only those powers with the same base. Okay, so if I have p to the second times p to the fourth times p, okay, we're going to simplify these. Okay, so just so you know, we're going to simplify these, which means we're going to work them down as far as they can go. So this would be p to the 2 plus 4 plus 1. So that makes this p to the 7th. Since we don't know what p is, that's the best we can do, so we'll leave it as p to the 7th. Problem number 7 here. Notice I have 2, 3, and 4. None of those are taken to exponents. None of them are the same base, but I can multiply 2 times 3 times 4. So I have a 2 times 3 times 4, and then I have a q to the 1 plus 4 and p to the 3, because you can only combine q's with q's and p's with p's. Okay, so 2 times 3 is 6, 6 times 4 is 24. I'm going to put these in alphabetical order because I like to do that. So I'm going to have p to the third, q to the fifth, because 1 plus 4 is 5. And there we have simplified that as far as it can go. Okay. Number 8 here. 4x to the fifth times 3x to the negative second means I'm going to multiply my 4 times my 3. And then I'm going to multiply x to the 5 plus negative 2. So 4 times 3 is 12. X to the 5 plus negative 2 is x to the third. And I am done at that point. Okay, number 9. Be very careful to watch all your negative signs here, including the ones in the exponents. So I have a negative 2 times negative 3 times negative 5. And I'll do my variables in alphabetical order. I've got a b to the 2 plus negative 3 and w to the negative 2 plus 2. All right, so that leaves me with negative 2 times negative 3 is positive 6. Positive 6 times negative 5 is negative 30. B to the negative first, w to the 0. Okay. Anything to the 0 power is 1, so that w tends to go away because 1 times negative 30 is negative 30. So this becomes negative 30b to the negative first. Now, numbers can be negative all day long. Exponents cannot. So the negative 30 is perfectly fine, and you can leave it in the numerator. But the b to the negative first has to move to the denominator to make it positive. So this would become negative 30 divided by b to the first, or just b. Now, you can use the property for multiplying powers with the same base to multiplying two numbers written in scientific notation. Now, remember, we did scientific notation several chapters ago, and you can use powers of 10 to make writing very large or very small numbers a whole lot more convenient. In scientific notation, you can write any number as a power of 10. For example, 256,000 in scientific notation is 2.56 times 10 to the fifth. Okay. So remember, in scientific notation, your first number has to be greater than 1, greater than or equal to 1, but less than 10. So it's got to be a number between 1 and 10, and then times the power of 10. So let's take a look at this problem. At 20 degrees Celsius, 1 cubic meter of water has a mass of about 9.98 times 10 to the fifth grams. Each gram of water contains 3.34 times 10 to the 22nd molecules of water. About how many molecules of water are in a swimming pool that holds 200 cubic meters of water? That's a lot of water, okay, especially when you're talking about molecules. All right, so let's see what we've got here. Let's give myself a little bit more space. 1 cubic meter of water has a mass of 9.98 times 10 to the fifth. So I'm going to write 9.98 times 10 to the fifth grams per cubic meter. Okay. And it says each gram of water contains 3.34 times 10 to the 22nd molecules of water. Okay. Each gram contains that. So 3.34 times 10 to the 22nd molecules per gram. I knew I needed the gram on the bottom because I needed to cancel out because it says how many molecules of water. I now have molecules per cubic meter, but I need molecules per 200 cubic meters, so I need to multiply this by 200 cubic meters. So now my cubic meters have canceled out. So now I'm left with just molecules. Now, if you want to make this super easy, I would change 200 to scientific notation. That would be 2 times 10 to the second, because I think that will be easier. So now what we're going to do is we're going to take 9.98 and we're going to multiply that by 3.34, and then we're going to multiply that by 2 times 10 to the 5 plus 22 plus 2. So if I multiply 9.98 times 3.34 times 2, I get 66.6664. Times 10 to the 5 plus 22 is 27, plus 2 is 29. But my answer is not in scientific notation, and it specifically said, write your answer in scientific notation. It's close. It's partly in scientific notation and partly not, because this 66 needs to change to 6.6. So this would be 6.6664 times 10 to the first times 10 to the 29th that I already had. So written in scientific notation, 6.66664 times 10 to the 30th molecules. So there are that many molecules of water in a swimming pool that holds 200 cubic meters. That's a lot of molecules of water. A very large number. Don't want to have to write that out. I don't want to have to move the decimal point 30 places to the right and add a whole bunch of zeros. So scientific notation is much easier for this. Let's take a look at another problem. The speed of light is about 3 times 10 to the 8th meters per second. How far would a beam of light travel in 8.64 times 10 to the 4th seconds? Okay, speed of light. 3 times 10 to the 8th meters per 1 second. How far would a beam of light travel in 8.64 times 10 to the 4th seconds? So far means we need to know this answer in meters. So we need to get the seconds to cancel out. So we're going to multiply it by 8.64 times 10 to the 4th seconds over 1. So now my seconds have canceled out, and now I'm going to have meters. So I'm just going to simply take 3 times 8.64 times 10 to the 8 plus 4. All right, 8.64 times 3 is 25.92. So I have 25.92 times 10 to the 12th, which is, again, not in scientific notation. It's in partially scientific notation and partially not. So I need to take this number here and move it to scientific notation. So it would be 2.592 times 10 to the 1st, because I made a big number smaller, okay, times 10 to the 12th. So this makes this 2.592 times 10 to the 13th. So how far will light travel in that time? Light will travel 2.592 times 10 to the 13th meters. Now, sometimes exponents can be expressed as fractions. Fractional exponents are called rational exponents. Now let's remember a few things. Remember that 3 squared is 3 times 3, which equals 9. You can write the same expression using a rational exponent, 9 to the 1/2. The equation 9 to the 1/2 equals b indicates that b is a positive number that when multiplied by itself equals 9. And 9 to the 1/2 equals 3, since 3 times 3 is 9. So in general, a to the 1 over m equals b means that b multiplied by a factor of m times equals a. And that's a little bit confusing until you actually start to work on the problems. So don't get hung up on the wording of this. Let's look at a couple of examples, and I think it will make sense. So let's simplify some expressions with rational exponents here. 32 to the 1/5. So we need to know what number, so what to the 5th power equals 32. That's what we're trying to figure out. Well, I happen to know that 2 to the 5th power equals 32. So 32 to the 1/5 has to equal 2. All right, let's take a look at this second one. 27 to the 1/3. So what to the 3rd power equals 27? What to the 3rd power equals 27. Okay, well, 3 times 3 times 3 equals 27. So 3 to the third equals 27. Therefore, 27 to the 1/3 equals, not 27 and 1/3, 27 to the 1/3 equals 3. The more you do them, the more you kind of understand how they work, and you can just play around with the numbers a little bit. Let's look at this third one, 64 to the 1/6. So what number to the 6th power is equal to 64? Well, 2 times 2 times 2 equals 8, and 8 times 8 is 64, so 2 times 2 times 2 is equal to 8. So 2 to the 6th is equal to 64. So 64 to the 1/6 equals 2. Now, they don't always have to be to the 1-something power, like 1/5, 1/3, 1/4. Sometimes you get numbers that are taken to an exponent like 3/2. Okay? Like 9 to the 3/2 power, which really means 9 to the 1/2 times 9 to the 1/2 times 9 to the 1/2. So if you look at each one individually, 9 to the 1/2 is 3. So you'd have 3 times 3 times 3, which is 27. Okay? So if I'm simplifying 4 to the 3/2, all right, 4 to the 3/2 is the same thing as saying 4 to the 1/2 times 4 to the 1/2 times 4 to the 1/2. So what number taken to the 2nd power equals 4? Well, that's 2. So 2 squared equals 4. So 4 to the 1/2 has to equal 2. So I have 4 to the 1/2, which is 2, times 4 to the 1/2, which is 2, times 4 to the 1/2, which is 2 again. So 4 to the 3/2 is equal to 8. Number 16. 16 to the 3/4. Okay, so I'm looking at something to the 1/4 plus 1/4 plus 1/4. So it's 16 to the 1/4 times 16 to the 1/4 times 16 to the 1/4, because 1/4 plus 1/4 plus 1/4 equals 3/4. So I now need to know what number to the 4th power equals 16. So 2 to the 4th equals 16. So 16 to the 1/4 is equal to 2. So I have again 2 times 2 times 2, which equals 8. The more you do these, the better you get at them. They seem a little confusing at first, but they will make sense later on. Let's look at 17. 3a to the 1/2 times b to the 1/2 times 3a to the 3/4 times b to the 2/5. Okay, here I'm just going to use my properties of exponents. 3 times 3. And then we'd have a to the 1/2 plus 3/4, b to the 1/2 plus 2/5. Well, you have to get a common denominator to add those. 3 times 3 is 9. This would be a to the 2/4 plus 3/4. B, common denominator there is 10. 1/2 is equal to 5/10. 2/5, 5 times 2 is 10, 2 times 2 is 4, is equal to 4/10. So we're going to have 9a to the 5/4, b to the 9/10. And we're done. All right, our closure question for today. How can you summarize multiplying powers with the same base? So summarize it in your own words. How do you summarize multiplying powers with the same base?